closer and closer and closer to x equals 1, what happens to the values of g of x? If I sort of draw my little lines here, what's happening to the values of g of x as I get closer and closer to 1? The values of g of x are getting closer and closer to what? They're getting closer and closer to 2. So, using our intuition and our definition of limit that we have, what do you think the limit of g of x is? It is 2. The limit here is 2. Now, what you'll notice is that's very different than the value of g of 1, right? The value of g of 1 from our definition over there says that at x equals 1, g of 1 should be equal to 0. Well, that's fine. The function value can be anything it wants at x equals 1. All I care about is what is the picture telling me? What can I see from this picture in terms of what happens to the values of g as I get close to x equals 1? It's not always going to be the case that the function's value at a particular a is equal to the limit value. It's not always going to be that case. This is one of those examples where it's not the case. Take a look at h of x. In that picture, pretty straightforward, hopefully. What's the value of the limit of h of x as x gets closer and closer to 1? It's equal to 2. And one thing you'll notice here is that that's the same thing as plugging the value of 1 into the function equation. That's an important property. This is something that has a lot of significance in calculus and something that we're going to utilize a lot as we move forward. It's always nice when we can just plug the limiting value into the function and get the same value as the limit. It doesn't always happen, as we saw with g of x. It doesn't always happen. When it does, good news. All right, now let's take a look at a couple of other limits. These will do. Yeah, that's fine. These will do sort of a little bit analytical. All right, so here we have some problems. The first one, we'll take a look at the limit as x approaches 0 of x. Second, the limit as x approaches 15 of 9. The third, the limit as x approaches negative 3 of x plus 2. All right. Really basic limit stuff. Okay. The first one, we're taking a limit of the function y equals x, where f of x equals x. We're taking a limit of that function. And I want to know what happens to that function as we get very, very, very close to 0. What happens to the function x as we get closer and closer to 0? It gets closer and closer to 0. Okay? This one is equal to 0. In a little bit of room that you may have left, let's imagine that we let it go to any value we want it to. Suppose x goes to a of, again, the function f of x equals x. What happens to this function? As I let x get closer and closer to any number I want, what happens to the value of x? It gets closer to that exact value I'm going to, right? This function, the function y equals x, has a limit value of whatever the x goes to. This is oftentimes called the identity function. It's nice in the fact that its limit is always equal to the limit of whatever you're going to. Okay? All right, what about number 2 here? I'm looking at the function y equals 9. And I want to know what happens to my function value. What happens to y equals 9 as I get closer and closer to the value x equals 15? Well, the function y equals 9 always has y value what? 9, right? So as x gets closer to 15, y gets closer to 9. The y function is not moving anywhere. It's staying at the same point forever and ever. Regardless of the x value you're giving me, the y value of this function is always going to be the same. We sort of generalize that a little further if we look at the limit as x goes to a of the function given by y equals a constant. That function is always going to have the same y value. It's constant. It's always at the same level. These are constant functions. The limit of a constant function is the value of the constant. All right, and then we come down here to this one, the limit as x approaches negative 3 of x plus 2. Well, x plus 2, what's the picture of that look like? It's a line, right? And the line is defined everywhere. And so if I want to figure this out, all I do is I take this x equals minus 3, and I let the x value here get very, 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 very close to minus 3. What happens to this function if we get very, very, very close to minus 3? This function gets closer and closer to minus 3. Now, we can take a look at that in a different way. This function, x plus 2, is made up of two different parts. It's made up of the identity function x, and it's also made up of this constant function, y equals 2. One of the properties of limits says that if I take the limit of the sum of two things, that's the same thing as taking the limit of each piece and then adding them together. And using the properties in 1 and 2 here, we see this is equal to negative 3 plus 2, which gives us the same answer that we got from the previous part. Okay. So limits have some nice properties that we can exploit, and that we'll need to exploit. And we'll give you what some of those properties are here in the next few minutes, and then maybe have time for a couple of more challenging ones. All right. Some limit laws. Try to stay consistent with the book, so I want to make sure I have the letters. All right. L, M, C, constant, no numbers. Okay. All right. And let me, suppose that g that are functions. First, if the limit as x approaches a of f of x equals m, and the limit as x approaches a of g of x equals L, then if I take a look at the limit as x approaches a of f of x plus g of x, what should that equal? I'm adding two functions who, as they approach a fixed value a, both of those functions have limits. If I add the functions before I take the limits, what should the new limit of that sum be equal to? What do you think? Go back and think about the problem we just did. Okay. You want a picture, look at a picture here. Okay, so f of x as x approaches a, both of these functions approach some fixed number, right? If I was to add the function f and the function g together, what would the limit of the two functions sum look like? They're really cool. Don't think of it. Don't try to think of what the graph of f plus g of x looks like right now. Think about just how we evaluate that. For all intents and purposes, that's the limit of f of x as x approaches a, right? This value right here is the value that f of x approaches as x gets closer to a. That point right there is the limit as x approaches a of g of x. If this right here just says add the two function values together, what's their limit supposed to be? This is L, or M, I guess. Did I say M? Sorry. If that's M, and that's L, how do I find f plus g of x? Add these two things, right? So the limit must have the same properties. If both of these functions have a limit at x equals a, if I add the two functions together and then take the limit, that's the same thing as taking the limits and adding them together.
Then would that be c?
No, c is a different constant that we'll get to in a minute. Okay? As a alternative way of writing this, this is the same as that limit plus this. Okay. Taking the limit of the sum of two functions is the same thing as taking each of the individual limits separately and then adding them together at the end. All right. Rule 2. Same hypotheses, limit of f of x is m. And c is a constant real number. The limit as x approaches a of c times f of x. So what I have is I have a function, and all I'm doing is I'm multiplying every value of that function by the same constant, whatever constant you want it to be. Pick your favorite number, multiply f of x by that number. If I'm doing that to every single value, if I want to calculate the limit of that new constant times f of x, what should I get? The constant here has absolutely no effect on this x plus a stuff. The constant is not affecting this part of my limit. So what I can do is I can pull my constant outside, because the constant is multiplying every f of x by the same value. And so it's not affecting how this limit is interacting with f of x, other than it's moving everything the same amount. And so in working with constants times functions, I can just move the constants outside of my limit, and that means this is c times m. So whenever I multiply a function by a constant, and I look for the limit, move the constant away for a minute, find the limit of the original function, then multiply that limit by the constant. And there's what we get. All right, and then I'll write the other ones up here real quickly. If I take the limit of f of x minus g of x, as x goes to a, that limit is m minus L. I can subtract limits. The limit of a difference is the difference of the limit.